I just realized I wasn't recording. Oh well, I think you got it. So work only includes forces that are parallel to the direction of motion. So no work is being applied to a box if the force is not parallel. Work uses displacement, not distance. Meaning that if you were to take your desk, go all the way around in a circle around the radius of the sun, or around the circumference of the earth, if you were to go all the way around, if your desk, if your desk starts in the classroom, and even if you travel all the way around the world with your desk and it ends up in the exact same spot, the total work on the desk is 0. Because we look at the initial position versus the final position. Also, this is a dot product, like torque uses a cross product. We get a scalar, which means it has no direction. So scalar is just a number with no direction. Vectors include direction. So let's do another example. Let's suppose we have a slope. Let's make this 60 degrees. We have a box. And let's say that the slope has a length of 10 meters. Box has a mass of 5 kilograms. And the question is, how much work is done on the box as it slides down the 10-meter slope? So this distance right here, 10 meters, 5 kilogram box. So we need to ask ourselves what forces are being applied on the box. Again, we'll ignore friction. There is only one force on the box, or I should say one main force acting on it. This would be gravity, mass times acceleration due to gravity. And we can break this up into component vectors. So we have a component vector like it pointed in this direction, and a component vector pointing in this direction. We also have a normal force. I'll just put it on the center of the box. We have a normal force pointing upward. So this would be the normal force. This angle right here, so this line right here is perpendicular to this line. This line right here is parallel with this. So it's perpendicular here, parallel with this. That means this angle must be 60 degrees. Which if we draw, we can also draw a line right here. That means that, anyway, I'm trying to think of the best way to explain it. I can never explain this. I just know that this angle is mg sine of theta, and this is mg cosine of theta. These two forces cancel each other out, giving us this is the only force being applied on the box. And if we were to deal with the work, we're only concerned ourselves with the force that is parallel with the direction of motion, and the box is just going to slide down the slope. So our force is going to be mg sine of theta times the displacement. The mass is 5 kilograms. G 9.8. I think on the homework I used 9.81 meters per second squared. That's the Newton. Times sine of 60 degrees. And the displacement is 10 meters. Which gives a total work of 424.7855 Newton meters. I also provided you with some cheat sheets. Yeah, that's one thing. So notice here, if you're pulling, let's say you're pulling a box with a string, the work is going to be F cosine theta d, because we only care about the parallel displacement, or the parallel force with the displacement. Here's another thing. So here's where theta is equivalent. So the parallel force is opposite of theta. There was another one that's so let's do another. Let's say that you have, so actually do that problem. We have a box, like 5 kilograms. Let's say we have a string pointing up at, let's make it 30 degrees, like this. And we carry it for a distance of 3 meters. So looking at our force, the box is going to move in this direction. So our force that is parallel with that direction would be the horizontal component, which would just be, and let's make this 20 newtons. So if this was 20 newtons, the parallel force, or horizontal force, would be 20 newtons times cosine of 30 degrees. So the total work would be 20 newtons times cosine of 30 degrees. And we traveled a total distance of 3 meters. But we're only concerned with displacement. In this case, displacement is equal to distance. But we'll only look at the initial position. We can call this the 0 meter mark. This is the 3 meter mark. And we get 51.96 Newton meters. So let's suppose let's suppose 100 Newton meters of work was done on a box, causing it to be displaced by 5 meters. How much force was applied to the box? And when given a problem like this, you can go ahead and assume that all the force, we're only concerned with the force that contributes to work, meaning just the parallel force. So what ends up happening is we have a box, we apply some unknown force to it, and it travels a distance, or it was displaced by 5 meters. We know that work is equal to F times D, so that means that force is equal to work divided by displacement. We were given 100 Newton meters of work on the box over a distance of 5 meters, which means we applied 20 newtons of force. We can also have a similar problem like this. A force of 10 newtons is applied to a box with a total of 50 Newton meters of work being applied to the box in total. So we have a force, and when given a problem like this where there's no real picture, you can assume that the entire force is going to be all parallel. We make these assumptions because it's ambiguous. Technically, what you could have is an infinite amount of force, because, or I should say near infinite, because if you had a force that is almost straight downward, if you had an infinite force downward and the box is moving to the right, your work is 0, right? And if you were to have the component vector to where only 10 newtons of force was to the right and infinite down, only the 10 newtons to the right matters. But when given a word problem like this where it's ambiguous, where the direction of the force is specified, we just assume that all the force is going to the right, because it's the only force that actually counts to the motion of the box, or the work. So we have 10 newtons going to the right. Question is, what is this displacement? What is the total displacement? So work is equal to force times d. If we're not concerning ourselves with direction and the force is all parallel, then we can just simply write this as force and displacement equal to work over force, or work was 50 Newton meters, or force was 10 newtons, so we traveled a distance of 5 meters. Seems fairly straightforward, right? Well, this gives us the reason why work is important because we have the work energy theorem. Work is equal to the change in kinetic energy. This is why work can also be written in joules because it's a change in energy. So we usually let work be Newton meters, but just know that 1 joule is equal to 1 Newton meter. So that means work is equal to final kinetic energy minus initial kinetic energy. And if mass stays constant, then work is equal to 1/2 mass times final velocity squared minus 1/2 times mass times initial velocity squared, because kinetic energy is equal to 1/2 mv squared. So this allows us to do some really nice things. We can figure out force required to do things. So, for example, let's figure out how much work is needed to push a 5-kilogram box. Let's make it 10 kilograms. A 10-kilogram box from 0 meters per second to 5 meters per second. We know that work is equal to the change in kinetic energy, or 1/2 mass times final velocity squared minus 1/2 times mass initial velocity squared. Note you can factor out the 1/2 and the m. So you can factor out that, and so it's the difference of squares. You don't have to. I just don't like writing 1/2 mass multiple times whenever you can factor. So that'd be 1/2 times, we have 10 kilograms. Our final velocity was 5 meters per second. Square that, minus our initial velocity, 0 meters per second squared. So that's equal to 1/2 times 10, or I should say that's equal to 5 kilograms times 25 meters squared per second squared, which would equal 125 Newton meters. Or joules. Question: is the same amount of work needed to go from 0 to 5 meters per second the same as the amount of work needed to go from 100 to 105? It takes significantly more work to go from 100 to 105 than it does go from 0 to 5. We could do that. So, work needed to go from 100 meters per second to 105 meters per second for a 10 kilogram box. We do the same thing. Work is equal to 1/2 mvf squared minus 1/2 mvi squared. So that'd be 1/2 times 10 kilograms times 105 meters per second squared, or the whole thing squared, minus 1/2 10 kilograms times 100 meters per second, all squared. So this represents the final, or this represents the final kinetic energy. This is the initial kinetic energy. So the final kinetic energy was 55,125 joules minus the initial kinetic energy, which is 50,000. So we get 5,125 Newton meters of work needed. This is actually why it's so hard to increase your speed. It's very easy to increase your speed at low speeds. To go from 0 to 5 miles per hour is very easy. But to go from 100 to 105 miles per hour takes a significant amount of work. Your energy has to be very powerful to increase your speed an additional 5 miles an hour if you're going super fast. We can apply something like this. So suppose 50 newtons of force was applied to a 5 kilogram box over a distance of 2 meters. If the box was initially traveling at 10 meters per second, what is the final velocity of the box? Now, we can solve this by realizing that F equals ma. This is a 5 kilogram box, 500 newtons of force. That means acceleration is F divided by m. So 50 newtons divided by 5 kilograms gives us an acceleration of 10 meters per second squared. We can then apply our equation that delta x is equal to vi times t plus 1/2 a times t squared. We don't know what t is, so we can't really use this one. We can use another kinematic equation and solve for it. I think the one would be vf squared is equal to vi squared plus 2 times a delta x. This is it. So final velocity is just equal to the square root of vi squared plus 2a delta x. We can plug these equations in and do it. What we can do instead is realize that work is equal to the change in kinetic energy. Or work is force times distance is is equal to the change in kinetic energy. So force times D is equal to 1/2 mvs squared minus 1/2 mvi squared. Solving for VF, we would add this to the other side, so force times D plus 1/2 mvi squared equal to 1/2 mvf squared. Multiply both sides by 2 over m to cancel out the m over 2. So that would be 2 times force D over m. That would cancel out this, so we get VI squared is equal to VF squared. Note that, so I'm going to rearrange this. So I'm going to move this to this side. And then I can take the square root. VF is equal to the square root of 2FD over m plus VI squared. No, this equation is actually the exact same as this. I just have the VI squared mixed up because F over m is A. So we get 2 times A times D displacement, and I get the same thing. So it's a little shortcut in case you forget the kinematic equations. Just notice the change in kinetic energy. So we plug that up. That would be the square root of 2 times the force of 50 newtons. Displacement is 2 meters. Divided by the mass of 5 kilograms. Plus initial velocity squared. And I get a final speed of 11.832 meters per second. Energy makes these equations a lot easier, and this just gives us a way to keep using energy with work. We can use this equivalent to find final speeds quite easily. I think there's one thing else I need to cover, and that is power. Power is the rate at which energy is produced or consumed. So power equal to energy over time. However, we're going to use this equation. Power equal to work over time. This is an equivalent equation. Remember that work is just a change in kinetic energy. And because energy is being produced or consumed, it's moving. And kinetic energy is the energy of motion. So another equation for power is work divided by time. The units of power is what? Units of power is the what? 1 watt is equal to 1 joule per second. Energy is in joules, time is in seconds, so this is equivalent. You've probably seen wattages before. So, for example, how much work? So let's say we have a 500 watt motor. That runs for 10 minutes. How much work did the motor do? Well, we know that power is equal to work over time. We can solve for work. Work is thus equal to power times time. Or power is 500 watts. Or time, note that we need it to be in seconds. So 600 seconds. And we get 300,000 Newton meters of work. More than likely, though, most of this work is going to be contributed to the flow of electricity. But in the actual spinning of the turbines, or whatever it's doing, I think that covers most of everything. We'll go over unique problems.